Hello, Coach Travis here, coming at you with another calculus video. So this is a fun application of antiderivatives here, an application to physics of antiderivatives. So what's happening? Okay, we got a van is cruising down the road and it's going 90 feet per second. And then it starts to slow down for some reason. I guess the driver starts applying the brakes, we'll assume. And so the deceleration of the van is 18 feet per second squared. And then we want to know how far is the van going to travel in 2 seconds. So 2 seconds after the van, after the brakes are applied, what's the distance that's going to be traveled by the van? So, I don't know, let's think about this for a minute. Yeah, I guess if the driver didn't apply the brakes at all, then after 2 seconds, then the van will have traveled 180 feet, because that's how fast the van was going. But that was if they didn't put on the brakes. So why am I doing that? I'm just kind of thinking, whenever you have a word problem, it's always nice to think about what's happening in the problem and kind of establish what's an upper and lower bound. So I know that when I get my answer should be less than 180 feet, because 180 feet would be how far the van would go if the driver didn't apply the brakes at all. But the driver is applying the brakes, so we are decelerating, so our answer should be something between 0 and 180 feet. All right, so let's do it then. So how are we going to do this? So the problem tells us about acceleration. So we're going to start with acceleration. That is, the problem tells us that we decelerate at a constant rate of 18 feet per second squared. So what that tells me what my acceleration function is. My acceleration is a function of time, and it's equal to negative 18. So let's think about that for a minute. First question, if I were you, the first question I might have is, where's the t? I mean, usually a function of time should have a time variable in it. But the key is it says it's constant. The acceleration is always an 18. So the acceleration actually doesn't depend upon t. So it makes sense that there's not a t here, because otherwise it wouldn't be constant. And then the other thing is, what's the negative doing here? Well, it's because we're talking about deceleration. So to me, it makes sense to make this a negative because the van is slowing down. It's not, if this were a positive 18, that would be an acceleration. But this is a deceleration, so we'll make it negative. Okay, so then what the heck are we supposed to do with that? Well, the idea is we know from physics or from previous calculus classes that there is a relationship between position, velocity, and acceleration. And in particular, we know that, we know that acceleration is the derivative of velocity. So that means I can get velocity out, I can recover velocity from acceleration if I do an antiderivative. So I want to do an antiderivative here, because again, acceleration is the derivative of velocity. So if I have velocity, then a derivative will get me acceleration. So if I have the opposite, if I have acceleration and I want velocity, then I have to do an antiderivative. And okay, well, the antiderivative of negative 18 is going to be negative 18t plus some unknown constant, right? Because when you find, you remember this, because t is the independent variable, And the antiderivative of a constant is just the constant times the independent variable. And then whenever you find an antiderivative, you have to have this plus c. Okay, but I think we can actually say more about c. Because let's just think for a minute about what's happening here. Notice, what do I get if I put 0 in for t into this velocity function? So if I just put in 0, I get negative 18 times 0 plus c. And that's, of course, that's just equal to c. So at time 0, c is the velocity of the car. Or maybe I said that backwards. What I should have said is c is how fast the car is going at time 0. And, well, time 0 is the moment when the driver applied the brakes. Because, you know, this experiment, I don't care what the driver's doing until they press the brakes. So I guess I should have written that down at the beginning somewhere. I should have said, and so I'm going to write it down now just so we'll be clear. Let t be the number of seconds after the brakes are applied. So if t is the number of seconds after the brakes are applied, then time 0 is going to be like the instant that the brakes are applied. And the problem says, oh, no, I did it. The problem says that at the instant that at the moment when the brakes are applied, the van is going at 90 feet per second. So we actually know that c is 90. So if you think, so I hope that made sense. If not, you can rewind the video and go through it again. But the point is, we actually know that the value of c should be 90, because 90 is the initial velocity of the van, and the problem tells me that the initial velocity of the van is 90. All right, good. So we got that. We're, slowly but surely, we're chipping away here. And again, you might say, Travis, why are you doing all of this? And this is a good question. Well, I guess one reason I'm doing it is because it's my homework problem. But maybe more specifically, why are you going through this process in order to answer this question? And again, the right way to think about solving problems is don't think about what you should do. Just think about what you can do. Just when you have a tough problem, just don't worry about what you should be doing. Just worry about what you can do. And so so I'm doing these things because I can. I know what the acceleration is, and then once I have the acceleration, I can figure out the velocity. And now that I've had the velocity, I bet I could figure out the position. All right, so the position function we know is the, I'm going to call it s. I guess because that's somewhat traditional to call the position function s. We know that velocity is the derivative of position. So that means that if I have the velocity and I want the position, again, I can do another antiderivative. And so, okay, so this is going to be now negative 9 times t squared, and then plus 90t, and then again plus an unknown constant. Because whenever you find an antiderivative, you do have an unknown constant. Okay, but just like we did before, through treachery and subterfuge, we were able to figure out what the unknown constant was for the velocity. And I bet we can for the position too. Because here's a pro tip. A pro tip is the plus c is always your initial condition. And when I say initial condition, I mean t is equal to 0. Because notice what happens. If we set t equal to 0, if t is 0, then this guy is going to be 0, and this guy is going to be 0. And all that you're going to be left with is c. So the moral is that the value of c is whatever if you're talking about velocity, then the value of c is going to be whatever the starting velocity is, whatever the time 0 velocity is. And if you're talking about position, then the c is going to always be your time 0 position. And so if I think about this problem, you might say, well, hey, Travis, the problem doesn't tell me where the van was at time 0. But if you think about what the question's asking, it's asking how many feet does the van travel 2 seconds after we press the brakes? And so the point is that we don't care where the van is at time 0. We just care where it ends up after 2 seconds. So the fact is, you can actually make this c any number you want, and it won't. You'll still get the right answer. And because the c is the starting position of the van. But to answer this question, the starting position of the van could be anything. It doesn't matter. They don't give us any information, and we don't need the information. So the simplest thing to do is let's just make it 0. Is just say that, yeah, like when I'm pretending I start caring about the van at the moment the driver presses the brakes. And so I'll just assume that the van starts at position 0, because that's where I start caring. Again, I hope that made sense. And again, feel free, after I get done doing this problem my way, go back and do the problem again, but put your favorite number here. Maybe your favorite number is 17. Go back and do this problem, but put a 17 there instead of a 0. And you'll see that you'll get exactly the same answer. Basically because the 17 will end up getting canceled out. So, all right. So let's see here. So now I want to know, how far does my van travel after 2 seconds? Okay, so now I have my position function. And the position function, that tells me about the position of the van. So, all right, so the distance traveled is going to be, well, it's going to be where the van is after 2 seconds minus where the van was at 0 seconds, right? It's like where the van started minus where the van ended up. And all right, so let's see here. Okay, so well, what do you get if you put 2 in here? If you put 2 in here, you get -9 times 4, and then plus 180. Okay, but then you have to subtract s of 0. Oh, but thanks to our choice of c, s of 0 is just 0. And now, actually, maybe you can kind of see now why we could put any number there. Because if we put a 17 there, then here we would get a plus 17, but over here we would get a minus 17. So it would just end up canceling out. So again, like I said, you can put any number you want there, it would still work out. Okay, and anyway, what do we get here? We get, that's -36. -36 plus 180, and so that's equal to 144. So all right, so the claim, and I guess that's in feet, I admit I did a bad job of carrying the units through this problem, but it should, we're talking about distance, and everything is measured in feet and in seconds. So our answer should be a distance, and distances in this problem are measured in feet. So that's what we get. So yeah, and does that answer make sense? We said that we should get an answer that's less than 180, because 180 feet is how far the van would travel if the brakes were not pressed. And sure enough, we got a number that's less than 180, and that's good. And it's not a lot less than 180, I guess, because only 2 seconds went by. So the van hasn't had a chance to decelerate that much. So it still goes pretty far. And all right, there you go.